This section, we're going to talk about a concept called partial, and then here's the keyword, derivatives. Now, your ability to do derivatives using the old techniques from calculus will directly impact your ability to do derivatives now. So there's literally nothing new to learn in this section other than you have to train your brain to see certain things as variables and certain things not as variables. But your derivative rules are your derivative rules. They're the same as they've always been. So let's start off. If I gave you this and asked you, hey, can you find the derivative? Could you do it? Pause the video. This should just be a review. Pause the video, give it a shot. Okay, so here we go. The derivative, first of all, notation-wise, we can either use y prime or dy dx because our output variable is y and our input variable is x, so that's why it gets that notation. Okay, and here we go. The derivative of x squared, well, that's a power rule. The 2 comes out to the front. And then you subtract 1 from your exponent, so 2 minus 1 makes 1, so there we go. Plus derivative of 3x, that would just be 3, because the variable has an exponent of 1, the 1 comes out to the front, making that x to the 0. Anything to the 0 is always 1. So this is really 3 times 1, but we just don't write that. So that's 3. Minus the derivative of 7 is 0. Why is it 0? Well, not because we memorized the derivative of a constant is 0. That'll get you into trouble. What we did is, we know that this is really 7 times x to the 0. Even though it wasn't written on the page, it's 7 times x to the 0. And the power rule says that 0 comes out to the front, which would result in 0 times 7 times x to the negative 1. But as we all know, I am quite certain that y dy dx equals 2. This is just a copy, x plus 3. 0 times anything always equals 0. So there's our answer. And right there, this is the key to getting this section right, to getting through partial derivatives and understanding what the heck you're doing, is understanding what is my variable. My variable is x. And does this term have x? Yes, it does. So I do my derivative. Does this term have x? Yes, it does. So I do my derivative. Does this term have x? No, it does not. So it really has x to the 0. And so it's 0 times the whole thing. Okay, so now, here we go. If I told you for this function here, now notice it has a z, an x, and a y. So do you see? And it's got a little interaction term that you learned about in the last section. If I told you x was the variable and y is a constant, find the derivative with respect to x. So what that means to me is we need to think of this. We can think of this as, if I just gave you this problem, y equals 7x squared plus 3 times x times 4 plus 4. Would you know what to do? Well, yeah, you'd probably simplify first and say 3 times 4 makes 12. So we'd rewrite this as 12. And now you'd have no problem. You would say, okay, 2 times 7, that's 14, x plus 12. This doesn't have any x's on it, so it's x to the 0, so that makes 0, right? This is the exact same thing. Just we have to train our brain because I just told you, y is a constant, x is a variable. So therefore, when you look at this, every time you see a y, you just think of it like the number 4. And so here we go. Now, the notation part, the z part, we'll come to in a second. Right now, let's just focus on the derivative. X is my variable. I have an x. It's squared. That's just a power rule. So this is going to be 14x. Plus 3 is a constant, y is a constant. What do you do with constants when you do a derivative? Well, you kind of just ignore them, right? You do your derivative of x to the first, which just turns out to be 1, and you take that number and multiply it by your constant. So I'd be left with 3y. Easy enough. Plus, now looking at this last term here, do I have any variables? No, I don't, because I told you x is the variable, not y. So therefore, this has x to the 0, so the 0 comes out to the front, and the whole thing becomes 0. So therefore, this derivative simply is, again, I don't know the notation to fill in here. We're going to come back and do that in a second. So it's just 14x plus 3y. Okay? Similarly, what if I told you y was the variable and x is the constant? Well, then we're going to do the derivative with, the verbiage is called with respect to y. So looking at this problem, again, we don't know the notation, we'll get there, but we're going to say, okay, does this have any variables in it? Does this term have any variables? Yeah, no, it does not, because it doesn't have any y's. So it's really y to the 0. So therefore, this whole thing becomes 0 plus. Now, again, our constant is a 3x because x is not a variable, y is. This is y to the first, so the 1 will come out to the front, giving us 3x, and that's it. And then last but not least, does our last term have any variables? Yes, it does. It has a y. That is y to the first. So that derivative, just the 1 comes out to the front, giving me 1. So my final answer here is 3x plus 1. That's it. That is the big idea to partial derivatives. That is the big jump, the big leap to section 15.2. So here we go. Notation. Now, in previous classes, you learned the prime notation, and you learned the Leibnitz notation, which is dy dx. Now, with partial derivatives, we're going to have very similar notations, except I can't use prime because I have to be specific when I'm showing somebody when I did the derivative here, which thing was my variable, which thing wasn't. If I just put a prime, you wouldn't know which was the variable. So what they've done is they said, okay, well, now our output function, instead of being z, so it'd be, in this problem, it would kind of be a z prime. Well, what we're going to do instead is we're going to say z, and instead of using a prime, what we're going to do is say, what was my variable? So if the variable was x, I'd put a little x down there. Or I might put a z sub y if y was my variable. So for this problem, my notation, since x was my variable for the first one, it would be a z sub x. And for the second one, it would be a z sub y. That would be your derivative notation. Okay, the other option we have is the Leibniz notation. Now this is really, really helpful for word problems. So don't just be like, I'm always going to use the other one. And especially because on a test, I might give you the notation. It may already be written out, so you got to understand it. So the D meant derivative, right? Well, I have to show that I was doing a partial derivative. So we just changed the D. We go to a delta. And they vary in their level of fanciness, but they look something like that. And now it's still the same basic idea though. Output variable, dependent variable, over the input variable. So it'd be dz dx or dz dy, but we would read this as the partial derivative of z with respect to x, or the partial derivative of z with respect to y. So again, the key word is partial derivative. Now, why is that important? Because you're telling the reader, when you use the word partial or use this fancy d or you use the z sub y notation, you're telling the reader that I treated all of my other variables as a constant. I pretended they were the number 7 and I only let y or x or whatever be my variable. It is absolutely crucial you use these notations, and when you speak of it, or if you write a sentence, you use the word partial derivative. You cannot just say derivative. Okay, so those are the big ideas. That's all we got right now, so I'll see you in the next video.